welcome to today's presentation on lightweight metallic fuel cells for portable and mobile applications. We have a little bit different approach than the other fuel cell developers here on the fair. First of all, I want to announce that we won the Industry Award 2014 here on the Hanover Fair yesterday, and we are very proud of that. And we also won in the end of last year the eZelleron Award, the most important German fuel cell award, and the Materialika Award 2013 for this lightweight full metallic fuel cell development. The outline of my talk is that I want to present you eZelleron, because most of you will probably not know us yet. I want to show you some of our product concepts and markets, and then about our technical progress in the last year, and about our future targets, and finally I will conclude. The company was founded in 2007 by myself. We have 25 employees. We have several strategic partners from industry and research, which we actually need. We have a broad network working together on the development of this technology. We have a broad IP portfolio of today 13 worldwide patent families, patented in USA, Japan, Europe, and China mainly. Several receipts, documents, and publications which protect our IP even more. And we had a pre-seed capital phase before the funding of the company of more than 8 million euros, seed capital phase of 3.1 million, and investments of partners in all around our technology field of more than 20 million euros. Short look at the patent portfolio. We have 2 patents already issued, one in Japan and one in the United States. The rest of the patents is pending at the moment. Most of them are published and will be issued in the next 2 years, and will protect us for the next 10 to 15 years. The financing cycle of eZelleron, we are still in the valley of death. As many startup companies, that's the phase where we still need capital. We don't have any income. There was equity capital invested since year 2003. We got a lot of funding, protection from European Union, from the state of Saxony, and also from German government, in form of non-repayable grants. So there are already more than 13 million euros invested in the company. From today until the cash flow positive point, we think we need about 4 million euros more. So you're all invited to invest. And after the cash flow positive point, here calculated with our first product, the eZelleron, we will be break even in 2018-19 and come in the profitable region. What markets are we heading for? I give you an overview of all the fuel cell markets, how we see them at last. On the y-axis you see the power level starting from 1 watt, 1 kilowatt, megawatt, gigawatt in a logarithmic scale. And on the x-axis starting from stationary to move to mobile and portable applications. We think that these markets, for example, power plants or small power plant CHP in the stationary market, cars and ships and aircraft in the moved market, and the camping, leisure, military and light vehicle region for the portable and mobile market have very different needs. For the power plants, for example, you need very high efficiency, long-term stability, several years of operation, and very rough cost targets. That's a high difference to what we do in the portable sector. There it's mainly needed that you have high power density, robust system, and quick startable system. All these challenges you don't need in the stationary sector. So it's totally different technologies needed for the different fuel cell markets, and in the portable sector you also don't need high efficiencies or long-term stability, because most applications only last for 3,000 hours, not for 100,000 hours like in the stationary field. So we think that our technology, which you will understand later on, is really the best for starting at low power levels in the portable sector, and then coming up to better cost targets, efficiency, and long-term stability markets. Why? Our USPs show it to you. We operate on available fuels like LPG, propane, butane, diesel. We have a quick startable technology. I will demonstrate it later on. We can start in several seconds. Solid oxide fuel cell, we are the only ones that can do that. That's the reason for the technology prizes we won. We are very lightweight because we have very high power densities, and that's the reason why we can also be applied in flying application like UAVs. And we have very low cost because we already now manufacture on mass manufacturing production methods, and we don't need any noble metals like, for example, in the polymer fuel cell field. This is a video showing you the quick startability in several seconds. I have a demonstration unit with me here. You can see it directly here on the place, and you can always come to our booth, B50, to see it. There is a combustion flame that heats up the cell, and it has to hit the cell, of course, otherwise it won't work. Sorry for that. There's a combustion flame that directly hits the cell. Part of the flame is reformed. That's the blue part of the flame. And the blue part of the flame is a free flow TPOX reformer making a hydrogen-rich gas. This gas goes in the inner side of the fuel cell, which is a tubular fuel cell, very small. And the rest of the gas is burned, heating up the fuel cell, and such a fuel cell can be heated up in some seconds then, and as you can see here, it produces electricity as long as the flame hits the cell. And as long as the burner works. To make it off. And this unit, for example, is already commercial. There is a provider, Lex Solar, that yesterday they started to sell the fuel cell demonstrator in their educational system. So it's an educational system for universities and schools where people can learn more about quick startable solid oxide fuel cell technology. Typically, solid oxide fuel cell technology is not available for schools because they need more than 4 hours of startup, and that's too long for a demonstration. So with our technology, that's possible. And what products do we want to make with it? Of course, not this, because this is just a very small market. We want to make power generators, like eZelleron, for example, a 1 to 2 watt system, mobile phone charger. I have one of them with me here. with that, you have already integration to charge your mobile phone. It is very there's isolation around the cell, of course. Then you don't need that much power as you need with such a flame combustor, and it has internal reformation and a total working system, allowing you to charge your mobile phone without ever the need to go back to the grid. You can see it here, you can have a look, you can come to our booth, again, B50, to see more about it. And with such units, for example, you can produce power by, this one is fueled by LPG. There's an LPG tank inside, and it makes power by a USB plug. The next unit is the eZelleron 2, already power levels of about 25 watt, strong enough to power a laptop continuously. And the eZelleron 3 is even for houses. It has standard plugs, and you can plug in almost every device you know. And it has also adapter for big LPG bottles, so you can run it for a very long time. But these units are still under development. I will show you later on the technical status. We also combine our cells to fuel cell stacks. Here you can see a 250 watt module, scalable technology. We can also build up higher power levels by combining several of these stacks. We have this stack now in a laboratory scale model, and maybe until the end of the year we will be able to deliver first units to customers. And furthermore, we do first projects on power to gas, because this technology is also very good in a reverse way. We can make gas directly from power coming from solar or wind energy. And there's a huge interest in that, and we are the only ones that can do that on peak load, not only on base load like the other fuel cell systems do. And that can be of high interest, especially for the solar technology. So again, the markets, we start here with portable applications like phones, laptops, going up to e-bikes, flying objects, boats, range extenders for boats or trucks, and finally maybe even primary drives for cars, propulsion, and aircraft. Comparing energy storage technologies, you have the ultra cap technology, batteries up to a lithium-ion battery, IC engine, combustion engine, and we are even better in terms of energy density and power density than a combustion engine can be, and we can also be scaled to levels where a IC engine cannot come to. That's the reason why this technology is very interesting for mobile electrical energy consuming products like e-bikes or cars, electric cars. You have to see that this is scaled in a logarithmic scale again, so it's a factor of 10 more than an IC engine. That's a lot. The state of our technology. I showed you already the cell. The cell goes into the market. The cells are ready, but with the cell, of course, you cannot earn a huge amount of money. You need a stack technology or a product. The product development of eZelleron is now in lab scale model mode. What you can see here is the first technology models coming now. So we want to have it ready to TRL 6 till the end of the year, starting field tests in the next year, and maybe get it market ready in the next year to start into the market. But as I showed you before, we need a a huge amount of invest to come there and to keep on track with this plan. The stack is in TRL4. With TRL5 you can start first system developments for the higher units, eZel2, eZel3, or even other applications like cars or whatever. What is this technology built? We have a small tube, 5 centimeters in length, 3 millimeters in diameter. On the inside you have the gas going through, on the outside you have air. You have different layers. The reason for the high technology knowledge we have is that we build up a lot of knowledge on these layers. That's one of the cores of our technology, because it's nanotechnology needed to manufacture these layers in the high qualities you need. We have a mass manufacturing line for it already. That's why I said it's ready for market. We produce everything on machines making a large scale. We can make thousands per day of the tubes. We sinter them, and we add the needed electrolyte layers and cathode layers on top. That's the cell manufacturing technology. You can learn more about our cells if you come to our booth, of course. And we have built almost everything with metals. So we have a cermet substrate. We have a metallic current collector on the outside and a cermet cathode. And we also can braze with metal the cells into the stack. So that's the reason for the quick stability, for the very good rigidness of the cells. And how to come there? I mean, we choose the best manufacturing technologies in terms of number of units and complexity of the workpiece. It's of course injection molding. We are the only ones that are able to injection mold fuel cells. The reason is that is not possible with commercially available binder systems, for example. We developed a whole new technology to make this happen, and we are the only ones that can do that at the moment. I presented a lot of technical background in the year 2012 about that. I presented a lot of background on the high quality of the electrolyte layers, which have grains below 1 micron at very low sintering temperatures in my last year's presentation here. I hope everyone has seen it, of course. And we have showed some tests on degradation behavior already in the last year, and that was the status of our problems. We had bad conductivity still in the cathode layer. That's why we now developed the metallic current collector, and we had brazing problems in the solders in our old hotbox design also. And these are quite new results showing you the improvements. These are the old GDC protection layers. This is a new one, much thinner, no more pores almost. It's a transparent layer now, not white as it was before. So we improved the quality a lot. You know, if you don't have any defects bigger than light wave, you will not see the defects anymore, because and the layers appear transparent. And this is a picture of our cermet cathode materials, which were developed in our cell department, and showing you the results on porous metallic cermet layers on the cathode side. Here you can see results presented already by Dr. Stöck. She was also on our booth B50. Maybe some of you have seen her. We had very high power levels with these composites, and we realized that we realized that after 100 hours we had a high degradation level, so the power came down a lot, and we improved the microstructure according to publications coming from Missouri University, Faith, and Ayan. I've seen Ayan also on the fair, I think. Very interesting results from the year 2012, and we included that in our cell manufacturing, allowing us to make a stable CERMAT cathode layer. So the cells behave good in stack environment. We have very high power levels. We can operate at high fuel utilizations even, and we are the only ones that have this thermocycling stable fuel cell. In this case, you can see 1,000 cycles. We can do more, but 1,000 cycles is for almost every application more than enough. And you have to keep in mind that a solid oxide fuel cell typically can be cycled about 10 to 15 times, not more than 1,000 times. So that's the reason why we are heading for these mobile markets. Stack power is also very high, and we have a very low stack weight. We have only 1.5% of degradation per 750 hours. We made a lot of work on system component development also, but we learned that with external combustors we are not able to quick start the cells anymore, so we had to introduce the combustion into the cell, which is typically also not possible. We are the first ones that do this in the microtubular world. It's possible because you can quick start and you can internally combust into such a fuel cell device, and that allows us a very higher integrated system architecture, which makes it much simpler. We just go in there with fuel and air, and we have just the off-gas and the electrical power on the output. We don't need a pre-start burner, which we have to control, controlling the temperature regimes, heating up over heat exchange of the stack, and so on. We don't need that anymore because we can internally combust. This is the power box, small stack. You can see it on our booth. And that's what happens always. The power is off, so we have to recharge. Just a joke, of course, to get you on track again. Showing you our products again. The eZelleron small unit can be weared in the pocket, ready to charge a smartphone. Internally, it's mainly a small hotbox unit and a lot of components, electronic components, and so on, coming from partners. The smartphone market is huge. Last year, more than 1 billion smartphones were sold. A lot of people, more than 10%, live in regions where they don't have access to the grid. It's not Europe typically, it's other regions like India, China, and so on. And there's a lot of people that need a grid-free power supply for their smartphones. According to the title of my presentation, some words about diesel. We made a lot of calculations on diesel for cars, and we have some projects already running with car manufacturers. With the eCell engine, of course, you can make a car that doesn't consume much diesel. A 2-liter car is possible. But you always have to keep in mind that development risk is still high. We are only on a very early development level of the stack technology, but we have a technology that in principle can do this and can provide quick startable, reliable power supply for cars. This is a concept then for a 90 kilowatt module. We think that we have a lot of advantages over a typical polymer system. because we have all the advantages of the solid oxide fuel cell with our FMFC system. We have the advantages of the solid oxide fuel cell and the advantages of a polymer system, like quick startability, high efficiencies, operation on hydrocarbons, and so on. And we don't have the restrictions that a polymer system has, and what is the main reason why fuel cell cars don't go into the market. Because they need platinum, which we don't need. They need hydrogen, which we don't need. And they need also a temperature regime where the polymer membrane can live, and that is typically not below 0 degrees Celsius. And we can provide all this for technology. It's a little bit shaked, this slide, sorry for that. We work on locally emission-free fuels, of course, but also on worldwide available fuels like LPG, kerosene, and diesel. But the diesel reforming technology is not at the status at the moment that it can be used for cars because it's not long-term stable. The best results shown in literature show 2,000 hours operation, and a car typically needs 3,000 to 4,000 hours, so it would be still a unit that has to be changed by service. Let me close my presentation with some words about the cost. We are already below 1,000 euros per kilowatt with the stack cost. We come below the cost of a polymer fuel cell, and with the first automation we could come even in the regime of the cost of a motor. So that makes it really attractive for different technologies that use motors at the moment, and with later generations we can probably even come below the cost of a motor because material costs are much lower than the cost of IC engine technology. I told you already we make power to gas conversion, and we are really focusing on the quick startable part, not on long-term storage. I have to conclude because my time runs out. We can make feedstocks in mass production. We can do cells in mass productions, stacks, hot boxes in small series production in a low technical level at the moment, but customer-made solutions. If you're interested for your projects, we can discuss on that. We make the first gas batteries in the next year, hopefully, and also can provide customer-made solutions on that. The same thing is with individual hybrid systems or power-to-gas conversion units. There is a lot of funding available at the moment, but we need always partner to come with us, to finance us, and to go into the markets. So cooperate with us, invest in us. If you're interested, talk to me or come to our booth B50. Thank you for your attention.